At Pasqal, we turn the quantum leap into a giant stride forward. The technology we've developed enables a whole new kind of performance. Let's find out how. Our system uses neutral rubidium atoms to perform computational processes. Each atom represents one qubit, the basic information unit of quantum computers. While in an ordinary computer, the state of a bit is 1 or 0, a qubit state can be 1, 0, or 1 and 0 at the same time. This property is called superposition. In our system, the atoms represent these states based on their energy level. At its lowest energy level, the atom's state is 0. When highly excited, its state is 1. When in superposition, its state is 1 and 0 at the same time. To use rubidium atoms for computing, we create a quantum register composed by multiple atoms functioning as qubits and make them interact using laser beams. Let's see how it works step by step. Vapor containing rubidium atoms is spatially confined by lasers acting like a trap. Another laser beam is shown on the trap. The beam is focused into multiple spots, so-called optical tweezers, to isolate and trap individual atoms. It's programmable to display the atoms in any desired pattern, creating a matrix. Each tweezer has one chance in 2 to trap an atom, leading to a partial filling of the pattern. To correct this and create a defect-free matrix, a moving tweezer is applied. It uses a stronger laser beam than the first tweezer, enabling it to attract atoms and to transfer them to the desired position. Using this technique, we can arrange the register into 1D, 2D, or even 3D geometries. Now that we have a defect-free register, we can start computing. In practice, this means causing the atoms to interact. We use lasers to raise an atom's energy level, causing it to switch from state 0 to state 1. When in an excited state, the atom starts to interact with neighboring atoms. This interaction sphere can reach several micrometers. If we then excite another atom from the matrix, the two interaction spheres will intersect, causing a reaction called entanglement. This process enables us to operate quantum gates. These are the basic building blocks of quantum circuits, used to perform computations. The case just described is a 2-qubit gate. We can go one step further and use one large laser beam covering all the atoms in the matrix at once. We will thereby create a collective interaction or a multi-qubit gate. This can be used to implement machine learning models on graphs. For instance, the quantum evolution kernel technique developed by Pasqal's team can be leveraged to solve complex real-world problems. Our groundbreaking technology represents a number of key advantages over existing systems. It already allows us to create quantum registers of up to 200 qubits and paves the way for a 1,000-qubit processor by 2023. The technology could also contribute to an improved environmental footprint. It functions at room temperature and will use up to 10,000 times less energy than current supercomputers. Ultimately, it could help to achieve universal computational mode, opening the way for exciting new solutions and mind-boggling new possibilities. Find out what's in it for you. Pasqal.io